Hi, this is the fifth lecture and of the topic vector integration. In the previous lecture, in the fourth lecture, we learned about the Stokes theorem, and at the end of my lecture, I have given you an important result. That is, if F bar is an irrotational field, then to identify it, we can uh, we can identify if a vector point function is given to identify it whether it is an irrotational field or not. So we have three things. One is the curl of f bar is a null vector, that is one. Or otherwise, if you find the line integral of f bar along a closed curve C is 0, then also we call that f bar as an irrotational field. And otherwise, if if there exists a scalar function phi, then that scalar for that scalar function phi, if you find the gradient, that should be the equal to the given f bar. If there exists a function phi such that f bar is equal to grade phi, even then also we say that f bar is a irrotational field, and this scalar function phi, we call it as a scalar potential function. That is one result what I have uh, given you. And another application of it is, if f bar is irrotational, as I said, it is the line integral of f bar along a closed curve C is 0. But if the curve is not closed, and if f bar is an irrotational vector, and what is the line integral of this f bar along a curve A, starting point is A and end point is B, then what could be the value of this integral? In general, if if you are given any vector point function f bar, this line integral uh, will depend on the curve what you are given. It's joining from A to B, along what curve these 2 points are joined, that depends on the curve what you take. But if you take f bar as an irrotational field, then whatever curve along whatever curve these 2 points A and B are joined, the line integral value is always same. And what is that value? As I'm saying that along any curve, the value, suppose if we have point here, whether I join it along this curve, or whether I join it along this curve, or whether I join it along a line, or whether I join it some other curve, even then also the line integral is same if f bar is irrotational. And what is that integral value? That integral value is, because I am saying that f bar is irrotational, definitely there will be a scalar potential, and the value of the scalar potential at B minus scalar potential at A. This is the value of that line integral, because I am saying that is irrespective of the curve. So whatever curve it takes along any curve, this value is always equal to FB minus FA. At that point of time, I stopped my lecture in my fourth lecture. Now, to have a better understanding of those things, I am going to solve few problems on the topic, and then I will move to the divergence theorem. So these problems probably I do believe that finding a scalar potential might have dealt by Srinivas Kumar in his lectures on fourth unit in vector differentiation, probably might have explained you how to find out the scalar potential. But however, again, I'm dealing the same topic here. Coming back to the examples, see the first example. Show that the vector field f bar is conservative. When do you say that the vector field is conservative? If the line integral joining from say line integral of f bar along a curve is 0, along a closed curve is 0, then it is we say that it is conservative. Otherwise, work done by f bar in moving a particle from A to B and again from back from B to A is 0, then we say that it is conservative. And find the scalar potential for it. And if after finding scalar potential, find the line integral of f bar, not along any curve, but he is asking from this point 0, 1 to this point 0, 2. So let us solve that problem. So this is the problem what he has given. Because he is asking us so that it is conservative, I'll find out curl f bar. I think you know how to find out curl f bar. Curl f bar is simply finding the uh, determinant. Curl f bar is the first row will be some I bar, j bar, k bar. Second row will be partial derivatives, and the third row will be the components. Here the component is x square plus xy square, and the second component is y square plus x square y. Third component is 0. If I find the derivative of first, if I expand this, this will be derivative with the of 0 with respect to y, that is 0. Derivative of this y component with respect to z, that is because here you don't have any z term, derivative with respect to z is also 0. Similarly, if you find the j with respect to j minus j bar into derivative of x with the derivative of 0 with respect to x is 0. Similarly, derivative of the first component, which is x square plus xy square, which do not include any z. Therefore, derivative with respect to z is 0. So, only thing if the coefficient of k bar, you will get it as derivative of the second component with respect to x, so that its value is 2xy, and derivative of this with respect to y, that is also 2xy. Therefore, 2xy minus 2xy, which is 0. Therefore, curl f bar is 0. By what the Stokes theorem says, the line integral of f bar along a closed curve is 0. Stokes theorem, we know that integral over c along a closed curve f bar dot dr bar is equal to integral over s curl f bar dot n bar ds bar. So curl f bar dot n bar ds bar, because this is 0, surface integral value, this value is 0. Therefore, in line integral along line integral of f bar along a closed curve is 0. That means the f bar is conservative. Whenever f bar is conservative, definitely there will be a function phi, which is what we call the scalar potential. Whenever this phi is scalar potential, the gradient of that phi is equal to the f bar given to you. This is my f bar given to you, and the gradient of phi, as per the definition, gradient of phi is I bar dou phi by dou x, j bar dou phi by dou y, k bar dou phi by dou z. So compare the coefficients. Here I bar coefficient is dou phi by dou x. Here also I bar quotient is x square plus xy square. So this is x square plus xy square is the coefficient. Therefore, x square plus xy square is this. Dou phi by dou x is this. Similarly, dou phi by dou y is the y bar quotient, that is equal to this. Dou phi by dou z, on the left side you don't have the k bar term. Therefore, dou phi by dou z is 0. We have three equations. Now you solve these equations. This is derivative is given this. Therefore, if I integrate it, I will get phi from it. What is phi? If I integrate this one with respect to dou phi by dou x, what in the first one, what I have is dou phi by dou x is x square plus xy square. And if I integrate this with respect to y, this is 5 times integral x square is x cube by 3. I am doing the integration with respect to x. Therefore, y is constant, x square y square by 2. And the integral of this phi we will get is simply by integrating this x square plus xy square dx. Now the constant of integration you will get. Here, because it is partial derivative, if you have some function of y or z, function of y and z, I will call it as f of yz. Even then, if I differentiate this with respect to x, I will get 0. Therefore, the constant of integration here need not be the real constant, may be any function of y and z. If you go back, if you differentiate this with respect to phi, with respect to x, again you need to get it. The derivative of this anyway you will get it, but the derivative of f, which is a function of yz with respect to x, is 0. So this is one possibility of your scalar potential. Similarly, so if I differentiate this first one, I'll get x cube by 3. So from this, I'm writing here x cube by 3 plus x square y square by 2 plus some function of yz I got. Again, differentiate this. If I differentiate this, what is phi? I'll get y cube by 3. So for the from the second one, I'll phi value will be y cube by 3 plus x square y square by 2 because I have to differentiate with respect to y plus some function of instead of yz, it will be some function of xz. What is dou phi by dou z is equal to 0? Then it will be the phi will be because I am getting 0. That means phi definitely will be a function of xy. So from this equation, this is the answer. From this equation, this is phi. From this equation, this is phi. Combining these two, I can take this as phi as this. Simply remember how to write it. X cube by 3 plus y square by 2. This part you write here. And in this y cube by 3 you have not written. Write that y cube by 3. X square plus y square by 2 already have written it. Therefore, don't write again. Only write once. Okay, it automatically satisfies these three. Let us see x cube by 3 plus x square y square by 2. This part, if I take, the remaining part will be function of yz. And if for the second one, y cube by 3 plus x square y square by 2, remaining should be function of xz. So this is my g, this is my g, this is my f, and this entire one is my h. So this is phi. Whenever you know phi, and let us take this P, this as the point P, this as the point Q. He is asking to evaluate the line integral of f from P to Q. As I said, whenever f bar is irrotational, then it will be grade phi, and the grade phi dr bar will be d phi. This is phi at Q minus phi at P. Phi at Q means substitute this Q in this phi. Q is your 1 comma 2. If I substitute 1 comma 2, this is 1 by 3. This is 2 square 4 by 2. 4 by 2 is 2. This is 1 by 3, 8 by 3, 8 by 3 plus 1 by 3, 9 by 3, that is 3. 3 plus 2, that is 5. First, this is 5 minus q at p. In p, x is 0, so these two will go out. This value will be there 1 by 3. 5 by 3 minus 1 by 3, which will be 14 by 3. So, line integral of f bar dot dr bar is 14 by 3. So, this is the first problem. So, coming to the next one. Yeah, show that the vector field is irrotational. He is asking us to find out whether it is irrotational. Also find this phi such that a bar is equal to grade phi. It is enough if you find out only the scalar potential. Here this part is not there. This is right. Here in this question, this part has not asked. Okay, a bar is this. Because a bar is this, curly a bar we need to find out to show that it is irrotational. Whenever you say curly a bar, this is first component, this is second, this is third. So first of all, the quotient of I bar, you have to find out the derivative of this with respect to, in the first one, you have to differentiate this with respect to y. Therefore, it will minus 4yz, and this with respect to z, again minus or minus plus 4yz, and if for coefficient of j bar, this is to be differentiated with respect to x, there is no x term, that is 0. This is to be differentiated with respect to z, there is no z term, therefore this is 0. And k bar coefficient, derivative of this with respect to x, that is 3x square, derivative of this with respect to y, that is 3x square. So everywhere it is 0, therefore it is a null vector. So don't write 0, it is 0 bar. Therefore, a bar is irrotational. When a bar is irrotational, we need to find out the scalar potential. If phi is the scalar potential, as I said, now the procedure is same. Grade phi we need to find out, and it is equate this to the given vector. Given vector is this, and equate this to grade phi. Compare the coefficients. Dou phi by dou x is 3x square y. J bar quotient is x cube minus 2yz square. This is dou phi by dou y. This is dou phi by dou z. From that, we need to find out phi. How you get this phi? You can easily understand that dou phi by dou x is equal to this. From this, what is your phi? The first, I will call this as 1, this as 2, this as 3. So what is your 1 implies? 1 implies phi will be, I need to differentiate this with respect to x. If I integrate this with respect to x, I'll get x cubed by 3, 3 and 3 gets cancelled, so that that value will be x cubed by. From 2, x cubed by plus what could be the constant of integration, because I am integrating with respect to x, it will be a function of the other two variables. From the second one, this is second equation. From this, you need to integrate this with respect to y, you need to integrate. Integral for x cube with respect to y is x cube y. And derivative of this y is y square by 2, 2 and 2 gets cancelled, minus y square z square. This is minus y square z square, plus constant of integration will be some function of x and z. From the third equation, what is phi? You have to differentiate integrate with respect to z. 3z square integral is z cube by 3, 3 and 3 gets cancelled. That will be z cube minus, if I integrate with respect to z, z square by 2, 2 and 2 gets cancelled. So if I integrate, I'll get y square minus z square. So, and the constant of integration will be function of xy. So the way how to write this phi, already I have explained you. From the first one, write down the function what you have, x cube y, remaining is function of yz. So this is all function of yz. And x cube already written, minus y square z square is there. So minus y square z square. In the third term, z cube is there. Of course, it is plus z cube, not minus z cube. Here you have 3z square. This is z cube. Minus y square z square. Already have written y square z square. Writing only one is enough. Here it is repeated. Wherever you have repeated terms, don't write. So this is your phi. He asked only phi, but no line integral. This is how we will find out the scalar potential. It is also of the similar kind. Uh, find the constant A so that this vector v bar, here instead of f bar he has given v bar, is conservative. If it is conservative, what is A? Whenever it is conservative, it is the curl v bar is 0 bar. Find curl v bar. If you find curl v bar, this is what you will get. When this will be null vector, each component is 0. So this is anyway 0. This also should be 0. This is 0 only when A is 4. This is also 0 when A is 4. So for A equal to 4, this is a curl vector. I think you will get this one by simply by finding the curl. You know how to find out this curl. So whenever A takes the value 4, then V bar is this. Simply put A equal to 4 here, 4xy minus z cube. And he is asking us to find out calculate the scalar potential. And already we have to find out the scalar potential. After that, work done. Work done is simply line integral from A to B. This is the point A, and the otherwise this is the point P, this is the point Q. So this is the given vector, and this is grade phi. Compare the coefficients. Dou phi by dou x is this. Dou phi by dou y is 2x square. Dou phi by dou z is minus 3xz square. Find what is from this is the first equation. This is second, and this is third. What is the first implies? What is your phi? Phi will be, I need to integrate with respect to y. Integrate x square by 2 in 4. 2 goes 2 times. So this will be 2x square y minus z cube x plus some function of yz. And what is the second equation? This phi is equal to, if I integrate with respect to y, I will get 2x square is constant, 2x square y. The remaining will be the function of x and z. What is the third part? Third one implies I need to integrate with respect to z. Integral z square is z cube by 3. 3 and 3 gets cancelled. Therefore, it is minus xz cube plus some function of xy. Combine these two and write it. 2x square y. In the second term also you have 2x square y minus z cube x that you have written. In the third equation also minus z cube x is there. And this is my phi. Once you got phi, then the line integral from a to b is simply equal to the phi value at q minus phi value at p. This is phi. Q is 1 minus 4 2. If I substitute 1 minus 4 2 here, minus 4 here, minus 8. And if I put 1, my 2 cube is 8. So this is another minus 8. This is phi of p, and minus the phi value at p. P is 1, 2 minus 3. Minus 3 whole cube is minus 27. So minus of minus plus 27. In this 1, 2 minus 3, this is 1, this is 2, this is 4. 4 minus 4 plus 27. And before that I have a minus sign here, therefore this is minus, this is also minus, and ultimately I'll get this minus 45, minus 16, minus 4, minus 20, minus 47, 47. Simplify this. This is how we'll get the line integral value. So that is what the Stokes theorem and some deductions of the Stokes theorem. If identifying a given vector as a irrotational vector by 3 ways, those 3 we learned, and also we learned how to find out the uh, scalar potential function for a given irrotational vector. Now we need to learn one more theorem, last theorem, that is the divergence theorem. For learning that divergence theorem, I need the definition of volume integral. This is very simple. And how do you define it? A volume integral. This is also just similar to the line integral and surface integral, what we have done previously. Now we'll define what the volume integral is. Suppose you have some closed surface and you have some region in space. This is my region E or R, whatever letter you use it. Divide that region into several parts. This is a, because it's a, if you have some region in space, some solid, if you have, we make that solid into several parts by cutting horizontally, vertically, and in the 3 directions, xy perpendicular to xy, yz, and zx planes. Then you will have a very small part. So several parts you will have. Take one small part. So this will have some volume. This is the, let us call that volume as delta VA. This is the ith subpart, and this is delta VA. In this region, you take one point UI bar. At this UI bar, find the vector point function f bar at this UI bar. Now you have f bar of UI bar and delta VI. Find this product and find that product for each and every element from 1 to n, because you made it n times. So you will get some value. Next, you increase the number of divisions. If I increase the number of divisions, what happens? The smaller, previously whatever smaller element you have, that will be further subdivided. So delta VI will be reduced. If you go on increasing the divisions, then delta VI tends to 0. Therefore, if limit as n tends to infinity, or limit as delta Vi tends to 0, both are same, this sum f bar of ui bar into delta Vi, if this exists, this limit we call it as volume integral. This is actually the definition, and we represent it the symbol integral over E f bar dv. Instead of the vector point function, if you take only scalar point function, you will take this phi value at ui bar into delta v. In that case, your volume integral will be integral over E phi dv. If you have a scalar function, this is phi dv. If you have a vector point function, then you have f bar dv. So both are this is another way of representing it. Triple integral over E f bar dv is dx dy dz. So this is simply if your f bar is fi bar plus gj bar plus hk bar, then your integral over f bar dv will be integral the small f, which is a function of xyz dv into I bar plus j bar times integral g dv plus k bar times integral h dv, or otherwise this integral can also be written triple integral f dx dy dz. This you know how to find out the triple integral for a scalar point function. If instead of f bar, if you are given only scalar point function, this is what you will get. So ultimately, if you have some region in space, the volume integral is simply if your function is a scalar function, say phi, it is phi dv. If your function is a vector point function, it is f bar dv. Or otherwise, the notation is triple integral phi dx dy dz. This will be you will have you'll have it will also have components. Each component is a triple integral. If your vector is, if you have a if your volume integral is for a vector point function, this is what a volume integral is. Ultimately, for the volume integral, you need to know how to integrate a triple integral. This evaluation of triple integral, you need to do it. This already on evaluation of triple integrals, I did some 3 to 4 lectures already uploaded to you in the unit 3. But for the chemical engineering students, they didn't learn this evaluation of triple integrals. The topic is not there in their syllabus, but still, I suggest you to go through the triple lecture 1 of the unit 3 given by me, and you also see that video and then follow the contents in it, and you will have an idea how to evaluate a triple integral that is required for solving the problems on volume integral. Okay, this is what volume integral is. Nothing much. Volume integral is simply evaluation of a triple integral. Just as a thumb rule, remember this. Volume integral is evaluation of a triple integral. How to evaluate a triple integral? I made 2, 3 videos. Go through them once again before solving problems here. Now, the last theorem of the vector integration. Already we considered 2 theorems. One theorem is Gauss divergence. Sorry, Gauss divergence theorem. This now we are doing. First theorem is Green's theorem, and after that is Stokes theorem. In Green's theorem, a line integral will be converted to a double integration. In Stokes theorem, a surface integral over an open surface will be converted to a line integral. Whereas in this Gauss divergence theorem, we have a conversion of from a surface integral to a volume integral. Before knowing all those things, let us see what actually the Gauss divergence theorem is. This is the statement. Read that statement. Yeah. If f bar whose components are small f, small g, small h, that is f bar is equal to fi bar plus gj bar plus hk bar, be a continuously differentiable vector point function defined on the region E. Region E is in the space. So a solid you have, a solid region you have in space, and at every point inside the solid, this function is defined. And because whenever you have a region in space, definitely there will be a boundary which is a closed surface. Yes. So you have a closed surface. Inside that closed surface, you have some region. So the surface integral of f bar dot n bar ds, if you want to find out the surface integral for that closed surface of this f bar, that is simply equivalent to the finding the volume integral of divergence of f bar, not for f bar. Find the divergence of f bar, which is a scalar point function, which is a scalar, and integrate over that region E. So that's what this Gauss divergence theorem says. Here n bar, as you know, it has same unit. N bar is the unit external normal vector to the closed surface S. That means yes, this is left side double integral over S f bar dot n bar ds means surface integral of f bar along the closed surface S. What the surface does, it covers a region E. Because that closed surface covers a region E is equal to, that surface integral is equal to the volume integral. Volume integral of what? Volume integral of that divergence of f bar. Where that volume integral is to be evaluated, that volume integral is to be evaluated over the region E. What is that region E? Region E is bounded by the closed surface S. Therefore, for applying Gauss divergence theorem, we need to have a closed surface. You observe here, I made in the different colors. For applying Gauss divergence theorem, you should have a closed surface and a region E. So the E is the region inside the closed surface. Yes, the the line integral of f bar over this closed surface is equal to volume integral of div f bar. Anyway, the proof is beyond the scope of the syllabus. I am not going to deal that in this lecture. If still anybody is interested to know about the know the proof, you can go through the books. It's very easy to understand. If you feel any difficulty in understanding that proof, you can ask me always. Divergence theorem. What this does, this converts a surface integral to a volume integral. Divergence theorem always converts a surface integral into a volume integral, whereas the first one, Green's theorem, converts a line integral to a double integral. In the Stokes theorem, you should have an open surface, the line integral to a surface integral. So that is the conversion. I think this is Gauss divergence theorem. Read it once again, the statement. If f bar is continuously differentiable vector point function defined on the region E, that region E is bounded by the closed surface S, then the line integral of f bar, surface integral of f bar over that S is equal to volume integral of div f bar over that E. That is what the divergence theorem is. From this, we will make some deductions. I think in the previous unit 4, you learned what a solenoidal vector is. A vector is said to be solenoidal if its divergence becomes 0. That already you know. So if you are given a vector point function, you know how to identify it as a solenoidal vector. You will identify a vector as a solenoidal vector by finding its divergence. If you find the divergence, if you get 0, then it is solenoidal, otherwise not. There are other means also to identify or to notify it as a solenoidal vector that you will understand from this divergence theorem. What divergence theorem says? Integral over S f bar dot ds bar. I think you know this notation also at the time of the f bar dot ds bar is equal to, it is same as f bar dot n bar ds. Whenever you write this n bar separately, ds you will write on f bar dot n bar ds is equal to div f bar dv, divergence of f bar. If f bar is a solenoidal vector, then div f bar is 0. Therefore, this value is 0. Therefore, integral over s f bar ds bar will be 0. So, what is the other way of, if anywhere for a function f bar, if the surface integral over a closed surface is 0, then we say that f bar is solenoidal. That is, the flux f bar along the closed surface is 0. Whether the flux, if I find the surface integral, I will get flux. That is the geometrical, that is the meaning or interpretation of a surface integral. So if the flux becomes 0, then we say that that vector is a solenoidal vector. Two things we learned. So other way is also there. You might have learned some standard results between curl divergence and the gradient. So among it, this is one standard. Divergence of curl v bar is 0. Whatever function is given to you for any vector point function v bar, if you find divergence and whatever you get, for that if you find for v bar, if you find curl and whatever you get for that, if you find divergence, then definitely you will get the value 0. Div curl v bar is 0, whatever may be v bar. If somewhere else, if f bar is, v bar is given as a very complex one, which is very difficult for doing derivatives also, and if you are asked to find out div curl f bar, straight away you can write it as 0. Div curl f bar means del dot del cross f bar is 0. Just now, we learned if f bar is a solenoidal vector, divergence of f bar is 0. If divergence of f bar is 0, then also we say that f bar is solenoidal. Divergence of f bar, if you just compare these two, in place of this f bar, you have this. So here I can say this is v bar. Div curl f bar, div curl f bar is del cross v bar. Okay. So therefore, if f bar is a solenoid vector, there exists a vector v bar such that f bar is equal to curl v bar. So if you are given a vector f bar and you are able to find out another vector v bar such that this f bar is equal to curl v bar, then also you will your vector is a solenoidal vector. Any one of these three ways we can identify a vector as the solenoidal vector. If a vector f bar is given to you, we can identify it as a solenoidal vector with any of the following, and these three are equivalent. With any of these three, we can identify them, and all the three are equivalent. If this happens, automatically this happens. If the one happens, automatically three happens. If three happens, automatically two happens, like that. What are those three? One is divergence is 0, then also we call it as a solenoidal vector. Other one is if there exists a vector v bar such that f bar is equal to curl v bar, then also we call it as a solenoidal vector. Third one is surface integral of f bar along that closed surface is 0. Surface integral of f bar along a closed surface is 0. Integral s f bar dot ds bar is 0. If any one of these three happens, then we can say that that vector is a solenoidal vector. The similar kind of thing already in the beginning of today's lecture I have given for irrotational. This is for solenoidal. These are the deductions on divergence theorem. Let us solve a few problems on it, and then we'll move further. So verify divergence theorem. This is taken over the cube bounded by this. We need to verify. Verification means both the things, both left side and right side, or surface integral and volume integral, both we need to find out and observe both are same or not. If they don't become equal, then that divergence theorem is not wrong, because we are going to verify that both should be same. Okay. So what is the function he has given? 4xz I bar minus y square j bar plus yz k bar. That is the f bar he has given. What divergence theorem says? Surface integral of f bar surface integral of f bar over this is equal to the volume integral of div f bar. These two have to find out. So I need div f bar. First I will find divergence of f bar. How do you find divergence of f bar? Divergence of f bar is the sum of the partial derivatives of the three components with respect to x, y, z respectively. These are the three components, 4xz minus y square plus yz. What is the 4xz derivative with respect to x? That is 4z. What is the derivative of minus y square with respect to y? Minus 2y. What is the derivative of yz with respect to z? It is y. So 4z minus y is the divergence. Now, let E is the region bounded by the surface. What is the surface he has given? He has given it as a cube. So this is the surface what is given to you here. So this is a cube. Yeah. This is the cube. Inside this cube, all that is the region E, and this is boundary is the surface. This is the boundary. Yeah, this is the boundary. Let us call the boundary. Yeah, this S is a combination of several surfaces. One is this is x-axis, this is my y-axis, and this is z-axis. I'll call this plane as S1 plane, which is z is equal to 0. Just opposite to that, I'll call it as S2. S2 this plane is z is equal to 1 plane. And this is the plane YZ plane. This plane is, I'll call it as x is equal to 0. This is S3. And this is the plane S4, and x is equal to 1. And this board is S5, which is equation is y equal to 0, and this front one, the projected one, is S6, which is y is equal to 1. So this is O, A, B, C, and this is D, E, F, G. So the S6 is DGBC. DGBC is the projected one. So these are several surfaces. Now you have, this is inside this, inside E, x varies from 0 to 1, y also varies from 0 to 1, z also varies from 0 to 1. This z varies from 0 to 1, x varies from 0 to 1, y also varies from 0 to 1. Okay, this is div f bar. Now I need to find out surface integral of f bar is equal to divergence of dv. This is what I need to prove. That is divergence of f bar is the integral over E 4z minus y dv, or triple integral over E 4z minus y dv means dx, dy, dz. So I need to evaluate this. I need to evaluate this. Both the values I need to show it are equal. So let us verify this. So remember, because instead of coming back again and again, remember this figure. The standard is this xy plane. I have given it as, this is xy plane. I call it as S1. S2 is just a plane opposite to it, that I call it as X2. Next, YZ plane, I call it as S3. Opposite to that, opposite to YZ plane, that is X is equal to 1, that is S4. S5 is Y equal to 0, and S6 is the projected one. So these are the, uh, this is the notation what I am using. So let us find out the, so first, because it is easy, I'll find out the RHS. But what is the RHS you have? You have RHS as triple integral over E 4z minus y dx dy dz. So that I will find out first. 4z minus y dx dy dz. In this, as I already explained, in that region, x varies from 0 to 1, y varies from 0 to 1, z varies from 0 to 1. This is x, this is y, that is z. So first integrate that with respect to x. Then what is that? You will get to 0 to 1, 0 to 1. There is no x here, so 4z minus y is constant into x. If I substitute the limits, that is 1. Next, dy dz. If I integrate with respect to y next, 4z integral is 4z into y. After substituting y, I'll get 1 minus integral y is y square by 2. After substituting the limits, I'll get 1 by 2 dz. Now, what is integral 4z? 4z is 4z square by 2. That is 2z. That is 2 minus 1 by 2. 1 by 2 into z. After substituting the limits, I'll get 1 by 2. 2 minus 1 by 2 is 3 by 2. So, triple integral value, I got 3 by 2. The same way, I need to find out the surface integral. So carefully follow how to find out the surface integral. Because the surface integral is equal to sum of these surface integrals. There are 6 surfaces, all put together, that is yes. So I have divided it. I'll find out this every integral separately. Along S1, first one, second, third, fourth, fifth, sixth. I'll find out one by one easily. So first I'll find out this second, third, fourth, fifth, and sixth. These values one after the other. Along S1, this is S1. Along S1, already I asked you to remember S1 is the XY plane, that is Z is equal to 0, And what is n bar for it? N bar, I said it is a outward normal vector. I'll go back to that figure once again just to say what about the n bar. So for this surface, what is the outward normal vector? This is z-axis. Along the z-axis, what is the outward? This is k bar is the normal vector, but this k bar is inside this one. Therefore, external one means the opposite to that. So in this direction is n bar for it. This in this direction, unit vector is minus k bar. Similarly, for this yz plane, the outward normal vector is minus I bar, and in this direction, that means for this plane, outward normal vector is I bar. Minus I bar is not for that. Similarly, for this plane, outward normal vector is k bar, not minus k bar. So in the similar way for J bar also. So you keep that in mind because remember n bar is always the outward normal vector. So for this surface S bar, n bar is minus k bar. So what is F bar dot n bar? F bar, uh, let us write F bar here once again. So F bar is 4xz minus y square yz. So here I will write 4xz I bar minus y square j bar plus yz k bar. This is my f bar. So now f bar dot n bar. What is f bar dot n bar? With this, if I make the dot product, n bar is minus k bar. So I'll get minus yz. F bar dot n bar is minus yz. Anyway, z is 0. Therefore, f bar dot n bar is 0. So here plus yz is. Yeah. Next is along S2. Second one, along S2, opposite to it, Z value is 1, N bar value is K, F bar dot N bar is YZ because Z is 1, it is Y. Integral over S2 I need to find out, not S1, integral over S2 Y ds. I mentioned ds we can write in many ways by taking the projection on any plane. I am taking this and the projection on xy by N bar by at the time of surface integrals I mentioned this y ds is dx dy by n bar dot k bar. N bar is k bar. K bar dot k bar is 1. Therefore, this is 1. Y dx dy. Limits are 0 to 1, 0 to 1. So if I integrate it, I'll get 1 by 2. Similarly, for each surface, for S3, that is yz plane, x is 0, n bar is minus I, f bar dot n bar is 0. For S4, x is 1, n bar is I bar, f bar dot n bar is here, n bar is I bar, 4xz. If I put x is equal to 1, 4z. For 4z, I need to do the integration. And what plane, if I am taking the projection yz plane, dz by n bar dot I bar. N bar dot I bar is 1 again, so it is 4z dz dy. So this value is 2. Similarly, for S4, S5, that is y is 0, n is minus j bar, this is 0. For S6, n is j bar, so f bar dot n bar is minus y square. So because y is 1, it is minus 1, integral minus 1 ds. So minus 1 ds is dz dy dz dx by n bar dot j bar. So minus 1 dz dx. So it is minus 1 if I limits are 0 to 1. So ultimately I got the value 6. First one is 0, second one is 1 by 2, 0, 2, 0 and minus 1. If I sum of these two, I will get 3 by 2. So even surface integral value also I got 3 by 2. And volume integral value also I got 3 by 2. If I the both are same, therefore Gauss divergence theorem is verified. So let us come for the next problem. Verify Gauss divergence theorem for the function f bar he has given like this or the cylindrical region bounded by this z is equal to 0 and z is equal to 2. So here what is this is x-axis, y-axis and this is z-axis. X square plus y square is equal to 9 is a cylinder which goes up to infinity and below also up to infinity. But here Uh, he has given z is equal to 0, which is xy plane, and another one is z is equal to 2. So this is z value is 2 here. That means you have a plane here. This plane is z is equal to 2, and you have another plane here. This plane is z is equal to 0. This is my region E, and surface is this curved surface, the cylindrical surface, this curved one, as well as the this plane z is equal to 0 and the plane z is equal to 2. So that is a closed tin, a cylindrical tin. That is the region here. Divergence theorem says here. This is why f bar you know. What is your divergence of our derivative of first component with respect to x, that is 0. Derivative of second component x with respect to y, that is 0. Derivative of third component z square with respect to z, that is 2z. So div f bar is 2z. E is the region, just now I explained, and in region inside the cylinder. The cylinder is x square plus y square is equal to 9, z is equal to 0, z is equal to 2. All the three equations put together, you have a cylindrical closed surface. Now the triple integral over div f bar means triple integral over E 2z dx dy dz. This I need to evaluate for triple integral. Simultaneously surface integral. We need to verify these two, surface integral and the line integral. So what is the RHS here? So coming back to RHS in the sense we need, this is RHS. Yeah. This we need to find out. This is RHS. And this is one divergence of February 2z dx dy dz. Now, I'm how to evaluate this triple integral. There are several ways I discussed already. Anyway, z varies from 0 to 2. Where x and y varies, x and y varies here. Where x and y here, what is this? This is a circle. What is that circle? X square plus y square is equal to 9. This is the circle x square plus y square is equal to 9 on the xy plane. So x and y varies here, z varies from 0 to 2. So I'll apply cylindrical polar coordinates. So x and y varies here. So here r varies from 0 to 3, theta varies from 0 to 2 pi, and z varies from 0 to 2. Or else, if somebody is not well known about the three triple integral of twin cylindrical polar coordinates, z limits anyway easy for them. It is 0 to 2. Xy limits are here on x square plus y square is equal to r square. For them, they can write y is equal to root 9 minus x square to plus root 9 minus x square and minus 3 to 3. 2z dz dy dx. In this way also they can do it, but it includes very integration becomes tough. But if you have idea of cylindrical polar coordinates, z varies from 0 to 2. This r varies in the circle x square plus y square, r varies from 0 to 3, and theta varies from 0 to 2 pi. 0 to 2 pi, 0 to 3, 0 to 2z. As I explained to you, dx, dy, dz, whenever you convert to spherical polar coordinates, Jacobian is to be written, that is r. Don't forget to write that r dz, dr, d theta. Now, if I integrate with respect to z, this is z square by 2, 2 and 2 gets cancelled. Z square will be there. If I substitute the limits, I'll get 4. And what is integral for r? R integral is r square by 2. If I substitute the limits, r square is 9 by 2 into, and d theta, theta is 2 pi. So 2 and 2 gets cancelled, therefore 9 pi will be remained. 9 pi into 4, that is 36 pi. That is right hand side. Now, let us see the surface integral. Surface, how many surfaces it has? I'll draw the figure once again here. Instead of going back, I'll draw this because it's simple. Yeah, this is the surface. One surface is z is equal to 0 surface. Another surface is z is equal to 2 surface. and the curved surface of this. Because this is a cylinder, you have a curved surface here. What is the equation of that curved surface? X square plus y square is equal to 9. If you know the surface, how to find out the normal vector? In our fourth unit, you learned once a surface equation is known, then by finding its gradient, you will get the normal vector. So we use those 3 points here. So this S is combination of three surfaces. What are those surfaces? One is the f bar dot in the surface S1, which is z is equal to 0, surface S2, which is z is equal to 2, surface S3, which is the curved surface. Along the surface S1, that means S1 is this, along the surface S1, n bar outward normal vector will be in this direction, which is minus k bar. And f bar dot n bar you know minus k bar, f bar you know, because if you know f bar, what is f bar dot n bar? If you remember the function yi bar xj bar plus z square k bar. So I'll write here yi bar plus xj bar plus z square k bar. This is my f bar. What is n bar, f bar dot n bar? If I find the dot product with n bar, what is n bar here? N bar is minus k bar. So it is minus z square. But on S1, what is z? Z is 0. Therefore, f bar dot n bar is 0. Therefore, that integral value is 0. S2, n bar is, what is n bar for it? Because for the surface, outward normal vector is k bar. N bar is k bar. F bar dot n bar is z square. Because on this surface S2, z value is 2, z square is 4. Integral S2 4 ds. So 4 can come out. Integral S2 ds. What is your ds? ds is dx dy. I mentioned here 4 times integral over S2 ds. ds can be written as some dx dy. Therefore, it automatically gives the area we already learned. What is that we have here? It is x square plus y square is equal to 9. What is the area of the circle? Pi r square. But r is r? 3. So 3 square is 9. 9 pi is the area. 9 pi into 4, that is 36 pi. In that way, we can calculate that. Now for S3. What is that S3? S3 equation is x square plus y square is equal to 9. How do you get the outward normal vector? By finding its gradient. How do you find the gradient? Gradient you will find a dou phi by dou x. You have to differentiate with respect to x, that is 2x I bar. Dou phi by dou y I bar, that is 2y j bar. Dou phi by dou z k bar, z is not there, therefore that is 0. By, because I want the unit normal vector, root over 2x whole square, 4x square, 2y whole square, 4y square. 4 if I take common, that is 2, I get root over x square plus y square. X square plus y square is 9. Therefore, that is 3. So, that n bar is, you'll get 2x I bar plus 2y j bar by root over 4x square plus 4y square. 4 if I take common, that will be 2 times root over x square plus y square. X square plus y square is 9. Therefore, this will be 3. 2 gets cancelled and xi bar plus yj bar by 3. This is my n bar. What is f bar dot n bar? N bar you know, f bar you know. F bar dot n bar is anyway 1 by 3 is there. Y into x, x into y. So dot product of these two, 2xy by 3, that is f bar dot n bar. Therefore, I need to find out integral over S3 f bar dot n bar, that is 2xy by 3. So 2xy by 3 ds, at the time of surface integrals, I mentioned clearly, while finding ds, I can take the projection on any plane. So here somebody, you may ask, why you are not taking the projection on the xy plane? As at the time of surface integrals, I clearly mentioned the the we take the ds can be written as dx dy by n bar dot k bar, dy dz by n bar dot I bar, dz dx by n bar dot j bar. That we can write how, when what circumstances we write. If you take the projection on the which plane, and the projection we take depending on our convenience. Here you may ask, if I take the projection, automatically projection will be on xy plane. Why I have not taken dx dy here? If I take dx dy here, in the denominator, what I should write? I should write n bar dot k bar, dx dy by n bar dot k bar. But if I write dx dy by n bar dot k bar here, in place of this, if I write dx dy by n bar dot k bar, so the problem is, what is your n bar? If I write dx dy by n bar dot k bar, this is my n bar. What is n bar dot k bar? I am getting 0. Therefore, in denominator I am getting 0. Therefore, I am not taking the projection on the xy plane. I am taking the projection on the yz plane. So this is y-axis, this is z-axis. If I take the projection of this on the xy plane, I will get a circle. But if I take the projection on the yz plane, I will get one rectangle. So if I just assume that there is a cylinder, a cylindrical tin is there. If you press it perpendicularly on the floor, the image will be a circular shape. Instead, if you press that cylinder on a wall, then you will get a rectangle. So that is what projection is. So if I take the projection on this, this is the projection of this on this xy plane, which is a rectangle. So 2xy dy dz by, you can take as well on the xz plane also, then also you'll get a rectangle. Now z limits we know 0 to 2. What are the limits for y? Y limits are, because you are taking the projection on the yz plane, your x will be 0. In x square plus y square, if I put x 0, y square is 3, y will be plus or minus 3. So if I take the projection on the negative side also, you'll have minus 3 to 3. Y limits are minus 3 to 3. X limits are, sorry, z limits are 0 to 2. 2 xy by 3 dy dz. Okay. But what is n bar dot I bar? N bar is this. N bar dot I bar is x by 3. So if I write x by 3, 3 goes to the numerator. 3 and 3 gets cancelled. X and x gets cancelled. That is why this 3 n bar dot I bar is x by 3. So that these 3 and 3 gets cancelled. X and x gets cancelled. Therefore here that x has gone, only 2y is remained, dy dz. What is integral for y? Integral that for y is y square by 2. 2 and 2 gets cancelled. Anyway, it's very easy. Minus 3 to 3, y is an odd function. Minus 3 to 3 odd function is 0. Straight away, we can put it. Therefore, for S3, it is 0. For S1, it is 0. For S2, it is 36 by. If I add all the three, for integral over s f bar dot n bar integral over s f bar dot n bar ds, this is 0 plus 36 pi plus 0. Ultimately, it is 36 pi. Here also I got 36 pi, here also I got 36 pi. Therefore, by Gauss divergence theorem is verified here also. Yeah. So next problem is this. Evaluate this xy bar y square j bar 2yz k bar, where s is bounded by x0, y0, z0, x plus y plus z is equal to 1. X plus, this is a very simple problem. X plus y plus z is, here he is not asking us to evaluate, he is asking to verify, only to, he is asking us to evaluate a surface integral over the closed surface. This is x plus y plus z is equal to 1. This is that plane. X plus y plus z is equal to 1. Uh, so this tetrahedron has three faces. This is one face, this is another face, and this is another face. Totally, you have four planes. That is, inside that there is the region E. The surface is also, you have how many surfaces? This is 1, 2, 3, and the triangular surface is 1. So totally four surfaces you have, but no need to finding that four surfaces. If you want to find the surface integral of f bar dot n bar ds, that he is asking us, because it's a closed surface. Since S is closed, we can apply divergence theorem. What divergence theorem says? Integral s f bar dot n bar ds is equal to this. Div f bar dv. F bar is this. What is divergence for it? Dou fi by dou x. If I differentiate this with respect to x, I'll get y. If I differentiate this with respect to y, I'll get 2y. If I differentiate this with respect to z, I'll get another 2y. Total is 5y. So this is equal to div f bar dv. This div f bar is 5y dv. Triple integral over e 5y dx dy dz. Here z is equal to 0 to this. So here z value is 1 minus x minus y. So, and if I take the projection region will be on the xy plane. Here only you require the knowledge of evaluation of triple integrals. Uh, this is the plane x plus y is equal to 1. Y varies from 0 to 1 minus x. X varies from 0 to 1. So 0 to 1, 0 to 1 minus x, these are the limits for y. Z limits are z is equal to 0 to 1 minus x minus y, 5y dz dy dx. First, with respect to z, if I do it, 5y is constant, integral dz is z. If I substitute the limits, this is dz dy dx. Now, just next with respect to y, I have to do. So this 1 minus x is another constant. 5 into 1 minus x is constant. Integral y I have to do. Integral y is y square by 2. Limits are 0 and 1 minus x. If I substitute 1 minus x whole square, so that 1 minus x whole cube by 2 minus 5y square is there, minus 5 into y square is the integral y square is y cube by 3. So 1 minus x whole cube by 3. So 5 into 1 minus x whole cube by 3 here, 5 into 1 minus x whole cube by 2 is here. If I take 5 into 1 minus x whole cube common, so 1 by 2 minus 1 by 3 is 1 by 6. That's how I got 5 by 6 into 1 minus x whole cube. Again, what is the integral for 1 minus x whole cube? 1 minus x whole to the power of 4 by minus 4 between the limits 0 to 1. Upper limit, if I substitute 0, if I substitute the lower limit, I'll get minus 1 by 4. Because it is lower limit, minus or minus plus 1 by 4. 5 by 6 already you have 5 by 6 into 1 by 4, that is 5 by 24. This is simple integration, that is why I have not expanded all the steps. So the surface integral value is 5 by 24. Yeah. The next problem is this. Apply divergence theorem. It's a very important problem and interesting. Apply divergence theorem to evaluate this. If you look at this one, you may be surprised what this is. X plus z dy dz, x plus y dx dy, yz dx dz. I have, at the time of surface integral, I didn't touch this topic. Very rare notation. Therefore, so far we learned in surface integral will be represented in this way. Integral f bar dot n bar ds, integral s, or integral or f bar dot ds bar. These are the two notations I have. This is also another notation. What actually this? So first, before going to solve this problem, I'd like to say something about this important note regarding the notation of surface integral. We know surface integral will be represented by f bar dot n bar ds. What is your n bar? N bar is the uh, outward normal vector that already we learned. N bar is the outward normal vector. Outward normal vector it is, and also unit vector, unit outward normal vector. N bar is the unit. I forgot to write here the unit. So if you know the DCs or DCs of a line, then they always L square plus M square plus N square is equal to 1. Or the DCs are, as per the definition of the DCs in 3 dimensions, you know that if a line makes an angle alpha, beta, gamma, then cos alpha, cos beta, cos gamma are the DCs. So DCs of a line are the components of the unit vector. That is the relation between the relay vectors and the 3 dimensional geometry representation. So I am taking this n bar as cos alpha I bar plus cos beta j bar plus cos gamma k bar. Cos square alpha plus cos square beta plus cos square gamma will be 1. So automatically every unit vector can be written in this form: cos alpha I bar, cos beta j bar, cos gamma k bar. And f bar is this. What is f bar dot n bar? F bar dot n bar is f into cos alpha, g into cos beta, h into cos gamma. F bar dot n bar. Now I need to find out integral f bar dot n bar ds. This is f bar dot n bar ds. That is, again I will have integral s f cos alpha ds, g cos beta ds, h cos gamma ds. And ds already I mentioned at the time of the surface integral. Ds can be written as dx dy by n bar dot I bar. Just I'll write here for your, just recall these things, or I'll write in a separate page. ds there we'll write it like this. ds is dx dy by n bar dot k bar, or dy dz by n bar dot I bar, or dx dz by n bar dot j bar. Easy to remember. Dx dy, this is the set I, j, k, x, y, z. When dx dy are there, dx dy is there, this k comes. Dy dz comes, dy dz is there, I comes. Dz dx comes, j comes. Dz dx by n bar dot j bar. So ds can be written in any of the three ways. So there I have integral over s f cos alpha ds. There I will write ds as dy dz, because this cos alpha is the coefficient for I bar. In n bar is cos alpha I bar plus cos beta j bar plus cos gamma k bar. Cos alpha is the coefficient for I bar. Quotient for I bar. Therefore, that I bar is here. Therefore, I'll take dy dz by n bar dot I bar. What is n bar dot I bar? Cos alpha. This cos alpha gets cancelled. So f dy dz you will get. So the first one is f dy dz. So f cos alpha, f n bar dot I bar, this is also cos alpha. These two gets cancelled, and f dy dz will remain. Similarly, the second one, this will be integral s g cos beta is there, dx dz, and this is h is, this one will become h dx dy. So that is what the surface integral s can be written ultimately. How do you write the surface integral? The integral over s f bar dot n bar ds can also be written as integral over s. For this, f bar will have one component f, that will be with dy dz, plus second component dz dx, third component h into dx dy. So if I combine with this integral s, f dy dz plus g dz dx plus h dx dy. So this is another notation. So if this is notation is given, how do you get this back? Dy dz quotient will be the I bar quotient. Dz dx quotient will be j bar quotient. Dx dy quotient will be k bar quotient. Thereby you will get f bar. Once it is given to you, you can automatically understand what f function is. So that is what this is equal to f bar dot n bar. What is f here? F bar is the first component is f, which is yz quotient into I bar. Dx dz, j, xz is there, therefore j is not there, put that j. Gj bar plus h dx dy is there, it is the quotient for k bar. Fi bar plus gj bar plus hk bar is the this f bar, if this is given. In this problem, this double integral, yes, surface integral is given in this notation. Once this notation is given, from this notation automatically you can find out what f bar is. What is f bar? I bar quotient is x plus z I bar, because dy, sometimes in the examination he will give this first, this next, this third, but don't take it in the order. You remember this. Dy dz will be the quotient of I bar. Dx dz quotient will be the quotient of j bar. Dx dy quotient will be quotient of k bar. Here dx dy is here the second, therefore x plus y k bar comes. Here dx dz is here y plus y plus z j bar, x plus z I bar. That is your f bar. Okay, coming back to this problem. So he is asking us to evaluate the surface integral, where S is the surface. What is that surface? Of the sphere. So here the surface is the entire sphere. As per this notation, F bar is x plus z I bar, dy dz quotient, y plus z j bar, x plus y k bar. This is equal to integral over S f bar dot n bar. F bar dot n bar is integral over v div f bar dv by divergence theorem. So integral over v div f bar. What is V? V is the region I have written here V. This is the V is bounded by the surface. What is div F bar? Because this is F bar, divergence is, what is your div F bar? Dou F by dou derivative of this with respect to X, derivative of this with respect to Y, derivative of this with respect to Z. So I got 2. So 2 dx dy dz. 2 if I triple integral dx dy dz gives the volume. 2 into what is the volume of the sphere? 4 third pi a cube. Already into 2 is there, therefore 8 by 3 pi a cube. So this is the surface integral value. So this completes the unit 5. I touched all the varieties of problems, but definitely I do believe that you will understand this topic easily if you practice more number of questions. We'll upload the questions also. You solve those problems. If you have any doubts or if you want to have if you require any clarifications on these topics, you can always call me on my mobile number 9490745460. But the thing is, because I don't have all your numbers, first of all, you put a message and then make a call. And otherwise, you can write an email regarding your doubt, and as far as possible, I'll try to clarify that by a reply mail. Otherwise, if you want to have any personal interaction, definitely I will make either a WhatsApp call or some other mode we use, and definitely I'll clarify all your doubts. With this, I completed the unit 5. Of course, I think all that vector calculus part, fourth unit and fifth unit are completed. For the other sections, except chemical, third unit is also completed. That means the syllabus is completed for all the sections except for the chemical engineering. Chemical engineering, third unit will be dealt by Srinivas Kumar. He will upload few lectures within few days. Then you follow those lectures. And my suggestion for the chemical engineering students is, though you don't have the multiple integration in your syllabus, go through the small video, especially made for you, just outline I have given, and for triple integration, follow the lectures uploaded for the other students. You also follow those lectures you also can access. So prepare well for the examinations. All the best. And if any doubts, you are welcome for clarifying your doubts. Good luck. All the best. Prepare well for the examinations.